So today we're going to start talking about Rd, that is, vectors of length d, each of whose components are sitting inside of R. We're actually going to recapitulate a large part of the class so far, talking about convergence and subsequences and so on, and lots of the theorems that we've already proved for R1, that is one-dimensional space, that is just the real line itself. And the reason we're going to be able to do that very quickly is that it turns out that we can sort of piggyback on the results that we have so far to prove lots of theorems by more or less just citing the one-dimensional versions or by copy-pasting, replacing a few symbols in a way that will become clear fairly soon. All right. Before we get to do that, though, we need to sort of write down our fundamental definitions, and probably the most important definition is the notion of convergence. And we sort of can guess what convergence should mean. I can draw R2 by pretending my computer screen is R2, and if I have some point A, and I think about a sequence converging to A, well, I more or less know what that means, right? I have the sequence following some weird squiggles, and after a while it sort of gets close to A and it sticks around that region and never leaves again. So in terms of drawing pictures, I think I'm sort of sorted. But when I come to write down a formula, it's not so clear what I should do. One thing that I could mean for an to get close to A is that every single component gets close to 0, right? All of the components get close. Another thing I could mean is the second formula here, that is the average distance gets close to 0. And you can imagine all sorts of other things that I could mean if I wanted to turn this sort of picture notion of closeness here into a mathematical formula. And it's not so obvious to me just staring at these which ones I want to do. And it's not so obvious for most of us. And so to try to answer that question, I'm going to sort of pull back for a step and talk about how people talk about distances in Rd and more generally in vector spaces. So the way that people talk about distances is they talk about some object called a norm. And a norm is a function from Rd to the non-negative reals that satisfies three properties, each of which I think are sort of a good property for a size function to have. So the first property is that if x is an Rd and the norm of x is 0, then x itself is actually equal to 0, right? So that makes sense. I don't want to say that an object has size 0 unless it literally is 0. The next property is linearity. The size of a number times x is just the absolute value of lambda times the size of x. And then finally, we have the triangle inequality, which we use all the time in doing computations. And so it's sort of nice to keep it here so we can use it. Okay. All of these notions here are meant to sort of generalize the absolute value sign. Okay. So for a large number of the proofs that we have, what you'll see is that if we had a proof that had the absolute value of A in R, we're going to have the same proof in Rd, except we're going to have two lines to tell us that we're dealing with a norm. And these three properties are really there to make that translation easier. That is, so that we can just copy paste a lot of the proofs and put the double lines there. So what are some examples of norms? Well, the norm that we've probably seen the most is Euclidean distance, and it's given by this formula here. And if we have to have a default norm, that's going to be the default norm for all of this class. There are other norms, and I'm going to get to some of them in a moment, and probably throughout this video you'll see that it's sort of useful to have them. All right, so that's the default norm. And if we go back, it's certainly possible to say, oh, right, the way that we just say that an converges to A is we want an minus A in the Euclidean norm to go to 0. So that's a third answer, different from answer 1 and answer 2. That's sort of a sensible answer to write down at this point. But it turns out that actually we don't have to make it a choice at all because of the following rather lovely theorem. If we have two norms, which I'll call norm A and norm B, then there exists some number C between 1 and infinity, not actually equal to infinity, which has the following property. C inverse times the norm of x with respect to A is less than the norm of x with respect to B, which is less than C times the norm of x with respect to A. What does that mean? It means that the norm with respect to A is basically the same thing as the norm with respect to B. Okay, except maybe you have to multiply by this constant. But the ratio, at least for x not equal to 0, this thing here is actually bounded. An immediate consequence of this is that xn converges to L, that is, the norm of xn minus L in the A norm goes to 0 if and only if the norm of xn minus L goes to 0 in the B norm as well. So if we're talking about convergence of norms to zero, it actually doesn't matter what norm we use. And so sometimes, depending on what calculation you're doing, it may be more convenient to use one norm or more convenient to use another norm. And this is telling us, yes, that's fine. You can use whatever you feel like if all that you're checking is that some norm goes to zero. Going back here, it means that actually all three of these answers are going to end up being pretty good. And in fact, all of them are going to be the same answer, even though they don't really look like the same answer. We're not going to prove this theorem in class. There are references in lecture notes to proofs, but they're sort of quite far afield from what we're mostly doing in this subject. So having checked that all of these norms are equivalent, or at least having seen that they're all equivalent, it's sort of nice to check that actually there are other norms that we can deal with. So here are a few that are popular. The first one is called the p norm. And for this, we have to assume that p is between 1 and infinity. And the norm looks like this. It's just the sum of the pth powers of the absolute values of the coordinates, the whole thing raised to the 1 over p. Then there's this thing called the sup norm, where the norm of x with the subscript infinity just means the maximum of xi. The Euclidean norm, which I wrote before, is one of these, and it's called the 2 norm. So it's exactly this norm with p is equal to 2. Furthermore, if you have some other norms that you've written down, linear combinations of those norms are norms as well, and there are lots of other places that norms come up. Okay, so there are a lot of norms sitting out there. These norms here are the most common in analysis and really the only ones that we're going to be using. All right, with that quick digression into norms out of the way, we can define convergence, and it's exactly what I wrote near the top of the video. We say that a sequence in Rn, xn, converges to some limit L, also in Rn, if and only if the norm of xn minus L goes to 0. And so the nice thing about all of this is that we get to piggyback on our old definition. That is, we don't need to do all of this sort of epsilons and whatever when we're defining here. We just say, great, this thing converges here, if and only if this other thing converges, and all of the epsilons are sort of hidden inside of that definition for convergence. Okay, we don't have to rewrite all of them. That's important to remember because that's going to let us rewrite a whole lot of our proofs without really getting into all of these sorts of messy details all over again. Let's see what that looks like when we prove an immediate corollary. What we're going to see is the following. If I have a sequence xn that converges to L and Rd, it converges if and only if all of the individual coordinates converge. Okay. So how do we prove something like this? Well, let's do one direction at a time. If xn is converging to L, then for all I between 1 and d, these coordinate things, xn over I minus L of I, those are bounded by the sup norm of xn minus L, and that thing's going to 0. So this thing goes to 0, this is bounded above by this xn minus L and sup norm, and so these things are all going to 0 as well, which means that xn of I is converging to L of I. So that's fairly quick. In the other direction, it's almost as quick. If xn of I converges to L of I for all I in 1, 2, up to d, then that means that xn minus L, this time in the 1 norm, is less than the sum of these coordinates. Now each of those is going to 0 by assumption, and so the sum of d of them is going to go to 0 as well by our arithmetic rules for limits. Okay, so this is quite a quick theorem, and you'll notice that even though we're talking about limits and so on, we didn't really have to get into any of the epsilon stuff. Most of our other definitions are going to piggyback in a way that hopefully is not terribly surprising. In particular, we're always just going to replace sequences by absolute values, that is norms, wherever we can. So let's talk about Cauchy sequences. So xn is Cauchy if and only if, for all epsilon greater than 0, there exists some n, depending on epsilon, so that for all mn greater than n, xn minus xn is less than epsilon. So this is exactly the same definition as we had in one dimension, but we replaced the absolute value by a norm. Okay. So it's a new definition, but you don't really have to think about it as a new definition. We're just replacing absolute values with norms, just like we did before. In one dimension, we had a really nice proposition, proposition 2.30 in the lecture notes, which says that a sequence xn converges if and only if the sequence is Cauchy. And that's one of the reasons to talk about Cauchy sequences. The same thing, unsurprisingly, is true in higher dimensions. And as a very short proof sketch, we're really just using the one-dimensional version of the theorem plus, going back up, this corollary here, which I'm going to refer to as star. So this corollary here says that a sequence of vectors converge if and only if all of their components converge. So the proof is really just using the one-dimensional version of the theorem plus that corollary, relating one-dimensional versions to high-dimensional versions. And I'd suggest that you turn off the video and try to check this for yourself, because it's not a terribly long exercise. Okay, I'm not going to stop because you can just pause for yourself, and I'll jump right into the proof, assuming that you've given it a shot yourself. So in the first direction, let's assume that xn converges to L. So when that happens, for all epsilon greater than 0, there exists some n depending on epsilon, so that for all n bigger than capital N, xn minus L is less than epsilon over 2. So this is, of course, just sort of the boilerplate in lots of our convergence theorems. So having gotten that out of the way, we do the calculation, and the calculation is a one-liner. That means that xn minus xm, oops, I forgot the norms, but let's put them in there, is less than xn minus L plus L minus xn, which is less than epsilon over 2 plus epsilon over 2, which is epsilon. So in this direction, there's really not much to do, right? So this is in fact the one-dimensional proof, except we have to add in the little norm signs instead of the absolute value signs. In the other direction, well, we start off with a little boilerplate as well. Since xn is a Cauchy sequence, for all epsilon greater than 0, there exists some n depending on epsilon, so that for all little m and n bigger than capital N, xn minus xm in norm is less than epsilon. And here I'm going to choose a norm. I'm going to be using the sup norm. Okay, great. What can we do with that? Well, since the sup norm is less than epsilon, then actually xn of I minus xm of I for any individual I is less than the sup norm, so that's also less than epsilon for every I. In particular, that means that the sequence xn of I is Cauchy for every I. All right. So at this point, we sort of related the big sequence, the sequence of vectors, down to the sequence of the individual components. And so now we can use the one-dimensional version of the sequence of the theorem. Since xn of I is Cauchy, that means xn of I converges to something which I'll call L of I. And by using the star theorem, since all of the individual coordinates converge, that means that in fact the entire vector converges. So this is actually not a terribly short proof when I write everything out, but just to sort of go over it, when I'm looking at the first direction, I have a bit of boilerplate, the boilerplate that I always have for convergence, and the rest of the proof, it's exactly the one-dimensional version, except that I have to throw norm signs where I used to have absolute values. In the other direction, I have some boilerplate again, and then I use the one-dimensional version of the theorem and this star theorem relating components to the full vector. Okay, so like I said, this was sort of my proof sketch, was just this one bit. And the rest of the work getting there is hopefully fairly routine. Okay, that doesn't mean you can do it in 2 seconds, but hopefully it's not terribly surprising.